So I'll be talking about programming with numerical uncertainties. And there's a few things I want to say before I start. So first, this work was done while I was at EPFL in Switzerland with Viktor Kunčák. Since then, I have moved to the Max Planck Institute for Software Systems. That's why there's the two logos. Also, this work chronologically comes before the talk, before the work that Viktor presented yesterday. So imagine the two talks in the other order. And finally, this talk is going to be a little bit more computer sciencey probably than other talks you've seen, so bear with me. So what do I mean with my title? This talk is going to be about implementing a real-valued arithmetic function. For instance, this approximation of a sign. Now, I don't really care about the truncation error here. What I really care about is just so this is exactly what we want to implement. Now, since we want to actually run this on a real computer, the first question is which data type are we going to choose? There's different options apart from exact reals. So if you want to actually run this fast, then we can either use a standard floating point data type, such as float or double, or we can use a higher precision data type like double-double or quad-double, which would be implemented in software, and that's why the running time is going to be much, much higher than for just regular floating points. Or you may be perhaps implementing an embedded system that cannot afford to have a floating point unit, so you have to choose a fixed point, some fixed point data type, and you may, for instance, have a choice between 16 or 32 bits as the bit length. These numbers were obtained on a JVM. So you can see that there's a difference in the runtime. And what I'm saying today is that I want to choose, always to choose the data type that is the fastest, because I want my code to be fast. However, this comes at a price, and that's what the black dots are. So there's some correlation. The faster the data type is going to be, the less accurate are the results going to be. So when you do the choice, you have to take into account both the cost in terms of efficiency and the accuracy. So what I'm interested is in programming with numerical uncertainties and doing this correctly. So this means that we need to take care of the round-off errors that we commit at every step, and potentially also input errors such as measurement uncertainties from sensors. Now, this was our original motivation, and since then, approximate computing became a thing, which essentially says, well, many applications are using way more precision than they actually need. So let's reduce the accuracy deliberately on purpose in order to save energy, memory, time, what have you. But you still want to know that your results are actually correct. So I'm first going to talk about a programming model that we proposed. Then I'll say, in a more technical way, how we estimate errors soundly and accurately. And then I close with how we can automatically improve accuracy. So what we propose is a real-valued specification language, here written in a subset of Scala, where the scientist writes the function with a real data type. So does not make the choice a priori which data type to choose. And in addition provides a specification. In this case, specifies the ranges of the one input, possibly an absolute error on the input, and the maximum error tolerated on the output. So why would you want to choose this? Well, first of all, this is essentially what a scientist will have in mind or written on paper. This is also what you may have proven correct, because the verification over reals is probably going to be easier than if you have to take into account finite precision semantics. It gives us an explicit ideal baseline against which we're actually computing these errors. So this is not something implicit, as usually left before. And this allows compiler optimizations that are sound, since you may know that finite precision arithmetic is not associative, so changing the order of the computation would not be sound with respect to finite precision semantics. But if we have reals, the compiler would be free to do that as long as the specification is satisfied. So, and then our verifying source-to-source compiler will come in that will then, depending on the specification that you provide, pick a data type, either one of the floating point data types, or it will choose a fixed point data type for you and generate the code for it. Does everyone know what fixed point arithmetic is, or should I quickly explain that? Should I? No? Explain? Okay, so fixed point arithmetic is something like floating point arithmetic, except that you have to determine at compile time where the decimal point for every value is. So if you have two floating points and you want to add them, then it's the floating point unit that will dynamically align the decimal points and then do the addition bit by bit. With fixed points, you essentially have to program this with the bit shift operators yourself. So it is a little bit more work at compile time, but you don't need the floating point unit. Our input language is Scala. Our output language is Scala 2. All the techniques I'll talk about later are completely language independent because all that we rely on is the IEEE standard for floating points, which is mostly satisfied by today's hardware. And if you want, you can try the code online. It's a research prototype, but I think reasonably stable. Victor can probably comment on that a bit more. Okay, so a source-to-source compiler that wants to select the data type will have to quantify the numerical errors so that it can make a choice which data type to choose. So we're not the only ones that are looking into this, so I want to put this a bit in context for you. If you're in numerical analysis, you may be able to do a manual analysis, which many times will be only asymptotic, so maybe two cores to actually make the decision between two data types, and you will need to essentially be an expert on this. Or you can do something like Sylvie presented. You can do this inside an interactive theorem prover, but again, this is at least partly manual and will require some knowledge about the theorem prover and the floating point arithmetic. On the completely other end, you have testing. So there's various approaches that will perturb the computation in various ways and can help you find bugs, however, will not give you any strong guarantees. So all of these approaches have some trade-offs. So what we are aiming for is a static analysis. This means it's fully automated at compile time with guarantees modulo bugs in the implementation. And the challenge then is to get reasonable accuracy in the analysis so that you can actually, you're not overestimating the round-off errors too much. So the goal is essentially have a static analysis which is sound, which is accurate, and which is fully automatic. So let's start with loop-free, branch-free code. So just straight line arithmetic turned out to be difficult enough. And we want to compute the absolute round-off, absolute numerical error. So this consists essentially of the worst-case round-off errors and the worst-case errors propagated that were on your inputs, for instance. Now it turns out that both of these depend on the ranges. So this means that you have to first compute the ranges of your intermediate expressions. So our technique is essentially abstract interpretation. So for each arithmetic operation, we'll first compute the real valued range. Then based on this, we can propagate existing errors. And based on this, we can compute new round-off errors. And we just repeat this for every operation. So this means we first need to get the ranges. And we want to get them as accurately as possible, because if the ranges are larger, the errors that we compute will be larger too. Standard choice that we also tried initially was interval arithmetic, which you all know suffers from the loss of correlations. Somewhat better is affine arithmetic, but again, if you have nonlinear operations, this may also introduce some over-approximations. And for us, this turned out to be a bit of a problem. So for one of the benchmarks that we got from the embedded systems domain was this jet engine, which is highly nonlinear, and then if your intermediate computations are too coarse, so in this case straddle 0, you try to divide by them, and you'll just get minus infinity to infinity. Or it may happen that you say want to compute the area of a triangle, but this formula is only valid if your triangles are valid, so you have this additional constraint in red. But neither interval nor affine arithmetic can actually take this into account. Now, one option would be to do interval subdivision, which is what another tool, so our competitor Fluctuate, does. Now, one reason why we don't want to do this is because we also want to cover fixed point arithmetic, and for this we actually need the whole range, so we cannot just consider sub ranges of the inputs. Now here the problem is written for interval arithmetic, but affine arithmetic has exactly the same problem here, and sometimes is even worse. So essentially the problem here is nonlinearity, and it's a problem for the range estimation, but also then for the propagation of the errors. So our solution was seemingly quite simple. So we're combining interval arithmetic with an SMT solver. We first compute the ranges for each intermediate expression again, first with interval arithmetic. This will give us a coarse estimate. And then we'll use the SMT solver to do a binary search and narrow down the range. The queries that we ask to the SMT solver are essentially, let's take this somewhat smaller range, is it still sound? And if the solver says yes, then we're happy, and then we just repeat. If not, then we take a wider range. So this was nice because this took care of all the correlations between the variables, no matter how nonlinear they were. And it allows us to add these additional constraints, like for the triangle example that I've shown before. And it also allows us, as a side effect, to do runtime error checks, because we do this at every step of the computation, and then we can essentially check at every step whether we're overflowing the data type or whether we potentially could divide by 0. We also have a check for underflow, because in our approximation of floating point numbers, we say underflow is an error, and this would also be checked by this procedure. Now, just to show you that this actually works really nicely, so I'm comparing here the simulated range, so that's the black bar, which is normalized to 1. The gray bars is what you would get with intervals. You see that 2 of them are missing because it just gave us minus infinity to infinity. And the red range is what our procedure provides. So this was surprisingly easy. I mean, I was surprised myself that this worked, but simple procedure. So that's the range. So let's go over to the error. So we're interested in the absolute error, and I'll use the following notation. So f of x without tildes is the real valued ideal function and input that we're considering. F tilde is the floating point or fixed point version, and x tilde is the actual input, which may include some additional errors. So we are separating this error into the propagation of initial errors and into the new round of errors that are incurred. And the reason for this is that one is essentially a global and the real valued property that depends on the full function. So if you're propagating errors, then you will do this even if your function is real valued in exact arithmetic. Whereas round-off errors are just the artifact of the finite precision. And we choose different methods to handle these, which give us a bit more accuracy. So for tracking the round-off errors, we use affine arithmetic, just as Fluctuate is doing. Essentially each, I assume everyone is familiar with affine arithmetic, otherwise scream. So every xi corresponds to more or less one round-off error, and at each step we're adding a new fresh xi that is computed from the ranges. Now this computation of the new round-off error is the only place in our technique that, that is different for each data type. So if you have your favorite new data type that has a different mantissa and a different exponent perhaps, then all you need to tell me is how to compute this new xi from the range, and then everything else will work as before. So for the error propagation, we're now looking at the same function, real-valued function, but with somewhat different inputs, and when we want to know how this changes the error. So the idea is, again, very simple. So we just take the Lipschitz constant from math. Just to comment on the difference to Victor's technique, so we're essentially taking the derivative with respect to the inputs, whereas I think in Victor's technique, he's taking the derivative with respect to the errors. So that's the main difference here. This gives you essentially the ability to magnify errors, and we report this number back to the user because it may tell him if the error is too large, which input he should look at to reduce the errors. We compute these partial derivatives symbolically. However, now we need to make sure that the k is the maximum k for all possible inputs. And we need to do this fully automatically. So for this, we again use our interval with SMT solver-based range computation, which gives us the accuracy because we now can take care of all the correlations over the entire function f, and it gives us the automation using the SMT solver. So now you could ask, well, now you have two methods to estimate these errors. You have affine arithmetic and you have this Lipschitz-based, so why don't you use affine arithmetic for both of them, for instance? So this is what we did initially, but we found that affine arithmetic was losing too many correlations, especially when the computation was nonlinear. However, affine arithmetic is fine if you have small errors, such as just roundoffs, because then the higher order terms will be even smaller and will not really make a big difference. Derivatives are nice if you have larger expressions, because then you can look at the correlation over the entire expression. So then we sort of did the compromise that we will use affine arithmetic to compute the roundoff errors for individual expressions. And these roundoff errors in the next step of the computation will become the initial errors, which will then be handled with the derivatives-based procedure. Right now we're relying on the user to write the code with these statements, but I think this is fairly natural because most people will just factorize their expressions anyway. Of course, you could try to do this automatically as well. It wouldn't be a big deal. Okay, so we're not the only one that have looked at this problem. More or less concurrently with us, Fluctuat was developed, which is mostly affine arithmetic based, and they treat the over approximations by adding constraints on the affine terms and by using interval subdivision. As I said before, this may not work immediately when you're considering fixed point arithmetic. A recent addition was this, the tool FP-Tyler, which takes a completely different point of view. So it constructs the whole expression with the errors and then takes a Tyler approximation of that and solves it with an optimization procedure. Real-to-float is essentially doing that, but with a different optimization procedure that can also provide better certificates. One thing to say, so I currently don't handle transcendentals, which is mostly due to the fact that Z3 doesn't handle transcendentals. You could imagine replacing the solver if you so want. And then you need to do a little bit more work on the affine arithmetic side. I do have an implementation for transcendentals and affine arithmetic as well. So if you have a motivated student, that could be done. To compare the results, so this turned out to be surprisingly difficult, so I'll have to explain this, this chart. So the top one will gives you the error difference between the different tools. The while scale is the difference within one order of magnitude. So the reason why I'm doing it this way is that the order of magnitude of the errors depends on how you have formulated the benchmark and not on the actual tool that is running this. So essentially, if it says 1, then this is a difference of 0.1 to the 10 to the minus 13, say, because all of the tools will generate an error of the order 10 to the minus 13. So the higher the bar, the bigger or the less accurate the error is computed by the tools. So I'm comparing here only to Fluctuat and FP Tyler because this work was done before Victor had his tool. And I'm considering 3 cases. One case where the benchmarks where we only consider the round-off error of the benchmarks. The second case is where we additionally have an input error, and the third one when we have a quadratic constraint on the inputs. So this is kind of the 3 scenarios I can imagine that an engineer would be interested in. FP Tyler in general produces the smallest errors, but does take a bit more time, which you can see on the second chart, which is essentially the analysis time in seconds. And note the y-axis is a log scale. I had to do this because once you add constraints, then FP Tyler may take a bit more time. So let me tell you essentially what I think about these results. So for straight line codes, the differences in the accuracy of the tools are very small. They're usually, as I said, 1 of the order of magnitude that the errors are. Comparing the run times is a bit difficult because these are 3 tools with 3 entirely different implementations implemented in 3 different programming languages, so it's hard to tell whether the difference of 3 to 5 seconds is due to the programming language or due to the technique itself. What's more important is that these tools have different asymptotic implementations, so with the choice which tool you want to use is going to be depending on exactly the kind of code you want to analyze. So for us, the bottleneck is the SMT solver. It may time out and may time out unpredictably. Although for the benchmarks we considered, we were reasonably happy with the performance. Fluctuat has very predictable times, so it'll come back to you within a second or 2. However, the accuracy may deteriorate once you have additional constraints on your inputs. And the interval subdivisions may not scale too much once you really look at larger codes. And for FP Tyler, you get potentially really large running times once you add constraints. So look at what your code does and pick your tool. That's my conclusion from this. So that was the nonlinearity. Now, a programming languages person would immediately ask, well, what about if-then-else statements? So suppose we have a function that is an approximation of an even more complicated function and subdivides the domain and does different approximations on the 2 domains, and then you have a decision y minus x, for instance. And then the question is, what happens when your real-valued computation takes a different branch than the finite-precision one due to the numerical errors? So this is what we call discontinuity error, and I think Fluctuat called it like that too. So let's look at the very simple case where the real-valued computation will take branch f1 and the finite-precision one the branch f2. So that's also what the expression says there. So we're again subdividing this error into this time 3 parts. The first one is essentially the amplification of the error in the if branch. Second one is the real value difference between the 2 branches, and then the third one is just the round-off error of the else branch. So our initial take on this problem was to do something similar, I think, than Victor, and just look at like essentially create a big constraint. But this doesn't scale when we use our SMT solver. So subdividing this error will introduce some over-approximation, but make the individual parts more treatable. And in particular, we have this real value difference separate, which in many cases is the major contributor to this discontinuity error. Now we use our Lipschitz continuity-based procedure for the first part, then the SMT-based range procedure for the second one, and affine arithmetic for the third one. But you could imagine replacing these if you have different procedures for each. So here I'm comparing against Fluctuat, which also has this procedure. The top chart is again the errors. This time it's just the absolute errors, but on the log scale. So we are generally more accurate than Fluctuat, but I do have to say that the interval subdivision did not work in this case. So Fluctuat can only look at the whole thing at once. On the other hand, our procedure takes longer, which is due to the SMT solver, mostly. Depends how much accuracy you need to pick your tool. Any questions so far? Okay. So then the programming languages person will come back to you, well, what about loops? So the trouble with loops is that in general the numerical errors will just grow with every iteration. With every iteration you will just add some more errors, so you cannot find an absolute error bound in general. One possibility is if you have a fixed bound on the number of iterations, you can use unrolling, which may or may not scale depending on the computation. Now our strategy was, because we found that for especially nonlinear computations, unrolling does not scale, we identified certain types of loops for which we could express the error as a function of the number of iterations, which we could compute fairly efficiently. And then if you give me your favorite n for the number of iterations, you just plug this in and then it's going to give you the error. So just to show you how this works, I'm going to use some more notation. So G is going to signify or stand for a function that computes the propagation error with our Lipschitz-based procedure, and sigma is going to be a function that can compute Roundoff errors. Now with some arithmetic, algebraic stuff, you can determine that if you have a, let's go back. So I'm considering here loops of, say, m iterations, and I'm considering only loops where the real-valued computation takes exactly the same number of iterations as the finite-precision one. Then you can derive this expression, which essentially tells you that you have to, for m iterations, you have to propagate the initial error m times, and then propagate the Roundoff error for each iteration m minus the number of times, which is not very surprising. Now this expression is not really helping us because the G and the sigma will potentially compute a different number for every iteration. So this was essentially amount to just unrolling, and we have not really gained anything. However, if we could compute a constant G and a constant sigma for all iterations, then we get a much simpler expression, which is then just a function of the number of iterations. So this works for something like this simulation of a pendulum, where we have approximated the sine function because we can't handle the real sine. And the one assumption that we make here is that the ranges of the variables that you're iterating over are bounded. So this allows us to look just at the loop body and analyze the derivatives once and for all, compute the Roundoff error once and for all for this loop body, plug it into our closed form expression, and then you have this function with which you can then determine the Roundoff error for a certain number of iterations. Now I think just having the numbers for the derivative and the Roundoff error could be also instructive for the programmer, so we also report this back to the user. And so just to give you an idea about the kind of errors that we compute here, so for this benchmark, for 50 iterations, we get an error of on the order 10 to the minus 14. So this is also something that Fluctuat can handle, but here it's kind of unfair, this comparison, because you do need to do unrolling. So we can scale up to 500 or even more iterations, and the analysis time in each of them is constant. It's 8 seconds. So I've talked about quantifying numerical errors for nonlinear computations, discontinuities, and loops. And just to summarize, before I continue with the other part, the key ideas that worked for us to make this work reasonably fast and accurate was to separate these errors into different parts, do a combination of interval affine arithmetic together with an SMT solver, and use analytical derivatives. Any questions so far? Okay, so one thing I haven't mentioned until now was that I assume for the analysis a fixed computation order. So I assume that the compiler is not going to go and change the order of the computation because that would change the errors, since finite precision arithmetic is not associative. So you can see this, for example, when you look at this. This is an embedded controller that was synthesized by Simulink MATLAB. And depending on which order of the computation you choose, the error is going to be, could potentially double, or the difference could even be larger. So in these two cases, I have just changed the order of the sum. So you could think that this is pretty bad. Now we said, well, let's exploit this, so let's go the other way. Let's reduce the error as much as we can. So let's improve the precision without actually changing the data type or anything else. This is nice because you can do this, if you can do this statically, then you can do this essentially for free. You'll pay a little bit analysis time at compile time, but then your code will run more accurately by not being slower. So this was joint work with Indranil Saha and Rupak Majumdar. And we considered in this work finite precision arithmetic, but the same ideas also apply to floating point arithmetic. It was just, they came from the embedded system side, so we're more interested in the fixed points. So you could try to enumerate all possible rewritings of the expression. This is quickly going to be infeasible. This is, so even for linear expression, you're going into the n factorial case. And the other trouble is that even if you try to optimize the errors locally, so you first try to optimize your sub-expressions and then go up, this may lead to a global, very large global error. So what we did instead was use genetic programming, but I was asked to quickly explain what that is. So essentially we're starting with an expression, and we're starting with the AST of an expression. And we start with 30 copies of it. Then we do we iterate for 30 generations. This is inspired by natural evolution, so that's why we have a population of 30 and 30 generations. And then in each iteration, we will pick out 2 ASTs. We will try to do crossover, which will generate 2 new abstract syntax trees, and then we will mutate these. So in every generation, we pick some expression rewritings, we will modify them in some way, then put them back, and just repeat. So the mutation is essentially associativity, distributivity, and the usual mathematical rules. For crossover, you take the 2 abstract syntax trees, you pick a random node in one of them, and try to find an equivalent node in the other so that you can switch the 2 subtrees in the expressions. We don't really implement a full decision procedure to check which ones are equivalent. We just label the trees and check the labels. So this is not complete, but it works reasonably well in our case. Now, the trick why this search procedure works is the way we select these trees. We select them based on a fitness function. So the fitter individuals in the population have a larger probability of getting picked for the next generation. And for this fitness function, we used our static analysis. In this case, we only used the affine arithmetic based so that it was fast enough to be repeated many times. Any questions? Yes?
What is the usual time that this kind of experiment takes?
This was on order of 5-6 seconds. So this was with the affine arithmetic-based static analysis. If we had thrown in the SMT solver, it would have run slower. So you want the fitness function to be reasonably fast. So however, if you want to use static analysis as a fitness function, you have to consider the over-approximations that the static analysis does. So in particular, we are now not interested in the absolute errors that the fitness function computes, but we are interested in how well it can discriminate when you have two expressions, which one has the smaller error. So you're not really interested in the absolute bounds, but you're just interested in which one is smaller. So we did some initial experiments to check whether our fitness function was actually reasonable. So this was for a linear benchmark, where the boxes are the errors that we analyzed, that our analysis computes for different rewritings. So here I think it was 50 different rewritings. And the diamond tells you what the simulated, so an approximation of the true error was. And you can see that these match very nicely. So essentially this says when our analysis says expression A has a smaller error, then it is likely that it will have the smaller error also in reality. However, for nonlinear expressions, the correlations were not quite as nice, which was sort of to be expected because our analysis is linear. But nonetheless, there is some correlation between those. So this leads me also to the guarantees that this method can provide. So we cannot provide optimality. First of all, because the search is incomplete, we cannot consider all possible rewritings. And the problem is at least in NP. And because of this problem that I explained to you, that the static analysis is doing over-approximations which may not really correlate with the errors themselves, we may not actually provide the best, may not return the best expression. However, the expression that our method does return is the one where our static analysis was able to prove the smallest bound, which may already be useful if you have an embedded system, for instance. So you may ask, why genetic programming and why not something else? We think it kind of works. So here I'm plotting over the different generations the analyzed error, the minimum error that was found, the maximum error over the population, and the average. And you can see that with every generation, the population sort of converges to these expressions that have smaller errors. So for the end-to-end experiments, our inputs were expressions that were generated by MATLAB Simulink from embedded controllers. And the error that we analyzed for this initial expression was sort of our baseline. And this shows the improvement on the error after we ran our search. So on the bottom line, the expressions get bigger to the right. And we could find that for larger expressions, we could improve the error by over 70% in many cases. As I said, this analysis runs within a couple of seconds, 5-6 seconds, and is fully automatic. So again, we were not the only ones that were looking at this problem. So Martel, and I'm not going to pronounce the name of his co-author, they developed an abstract domain that could represent an under-approximation of the possible rewritings, because again, you cannot look at all of them. However, they only looked at optimizing the bit length, whereas we had a fixed bit length and tried to optimize within that. And they only did a local search, so there is a question how good these how good the results were. More or less concurrently with us was the work by Eldip and Wang, who used an SMT-based synthesis. So they provided sort of a skeleton to the SMT solver, and the SMT solver selected which parts of the skeleton would be put into the final functions, but they could only consider linear expressions because of the limitations of the SMT solver. And again, this was just a local search because the SMT solver can't handle the whole thing. More recently was a tool Herbie, which was pretty cool, however, only testing-based. So they considered a testing-based procedure, and they looked at the average error, which I'm not quite sure why they did that. So they had some success by improving expressions from some mathematical libraries online. And one thing that they also provided was this regime inference. So you may, one expression, one rewriting of an expression may not be optimal for the whole domain of your function. So you may know the formula for the triangle, which depending on what your inputs are, it will select a different formulation. So they were trying to synthesize these different formulations for different domains. But again, they could not provide any guarantees. It was testing based. Okay, that brings me to the end of my talk. So the conclusion is that, unlike what we thought initially, quantifying numerical uncertainties was hard. For us, what worked, it was a combination of different techniques plus the advances in SMT to get the automated and accurate results. Thank you.
When you use Lipschitz constants, so one way to do Lipschitz constants is to have a lower and an upper Lipschitz constant. So instead of saying that you're bounding the absolute value of difference, you just bound the difference, but from both sides, and then you can have different Lipschitz constants. So instead of, if you imagine the Lipschitz constant sort of gives you a bow tie, and if you have two Lipschitz constants, you can make this bow tie much narrower in certain situations. Are you using any kind of thing like that, or just usual Lipschitz constants?
So we're just using usual Lipschitz constant because we're considering worst case Roundoff errors, and we don't really have information of which errors will be on the lower and on the upper end. So I'm not sure how this could be combined with the worst case errors. But
no, so for example, the Lipschitz constant, no, it only depends on the function, right? So if you take the sine function, if it's in some area where it's around 0, you can tell that the Lipschitz constant is slightly, say it's 1, or maybe a little more than 1, but the lower one then can be something like 0.9. And so then you know very precisely. Anyway, it's an idea that has been exploited in a couple of places, and I just wanted to mention it. It may give you something.
Okay, perhaps we can talk later, because I'm still not sure how you would do this with worst case analysis.
I have a very naive question. I mean, you mentioned when you use the Z3 SMT solver. So what makes an SMT fits for you? I mean, what are the criteria for selecting a particular SMT solver?
So we're using actually the NLSAT solver within Z3, which is implementing a version of cylindrical algebraic decomposition. You could imagine using a different solver. What we need is that the solver can answer us when our queries are unsat, or when they're unsatisfiable. So that's the criterion that we require the solver to do. Why we chose Z3 in particular was the interface was already there, so it was easy for me to use it. And it's one of the few SMT solvers that actually have a nonlinear decision procedure implemented. In principle, the theory is decidable. In practice, the solver either will return immediately or not at all, which makes it nice because then you can have a small timeout.
Other questions? So could you comment on the relation to formal verification? So you find, I mean, you're using genetic algorithms and SMT solvers to find algorithms. So would you, in the end, verify only those algorithms, or would you recommend verifying the whole process?
So for the round-off error estimation, I think it would make sense to verify the underlying algorithm, probably not the code itself. The trouble there would be the solver. So either you can somehow get a certificate out of Z3, which currently I think is not feasible, or you choose a different decision procedure or a different solver in that case that can provide you these certificates. So I think then that would be a reasonable way. For the genetic search, the genetic algorithm, this is an inherently heuristic search. So that's probably not something you want to formally verify, but you may want to verify the end result's accuracy. Now, as I said, the search is incomplete and is necessarily incomplete because you can't look at all of them and there's no gradient or something to exploit. So all you can say is, for the expressions I looked at, this is the best.
Another question? No? Okay. Thank you.